this lesson, we're going to be discussing probability distributions. So a couple definitions just to get us started here. A random variable is a variable whose value is determined by chance. And then a discrete probability distribution consists of those values of the random variable, as well as the probabilities that correspond to them. Taking a look at our first example, we're going to construct a probability distribution for just rolling a single die. So we're going to think about the outcomes when we roll a single die, and we're also going to think about the probability of getting those outcomes. So if we think about rolling a die, we could roll a 1, 2, 3, 4, 5, or 6. And then the probability of rolling a 1, there's just a single 1 on a die out of 6 possible outcomes. That probability would stay consistent throughout this entire distribution because there is only 1, 2 on the die. There's 1, 3 on the die, so on and so forth. So it is a constant probability distribution. So if we were to graph this, listing those x values across the x-axis, those are our random variables. And then the probabilities, I'm just going to put 1/6 right here because they are all the same. We would see they have the same height the entire way across. So we have that constant distribution. It is symmetric, but because they're all the same value, we say that it's constant. Okay, the next example that we're going to take a look at is for tossing 3 coins and counting the number of heads. Okay, so if we think about our x values representing the number of heads that we could toss if we toss 3 coins, we could get 0 heads, we could get 1 head, 2 heads, or all 3 heads. This probability of getting 0 heads, we do have to remember that we're tossing a coin 3 times. So if we don't get any heads, that's the same as getting 3 tails. So the probability of getting a tail on the first toss would be 1/2. That would stay consistent for the next 2 tosses because those are independent events. So we would be multiplying 1/2 times 1/2 times 1/2, or that would be 1/8. We could also jump over here to the 3 heads scenario, and it's going to sound familiar from the work that we just did, except for getting all tails, we're going to get all heads. But because a coin is equally likely to be heads or tails, we get the same answer, 1/8. But if we were to assume that we got the same answer for these 2 as well, notice that our probabilities would only add up to 4/8 or 1/2. So we have to be careful on these middle 2 scenarios. So if we think about just getting 1 head first, we could get a head on the first toss and then followed by the 2 tails, but that's not the only order that we would want to include because we could get the head on the second toss, or we could get the head on the third toss. Each one of those is going to be the same, 1/8 probability. But because we could have the 3 different orders, we would add these 1/8 together. So the probability of getting heads on the first toss is 1/8, or the second toss is 1/8, or the third toss is 1/8. So we actually have 3/8 because we have 3 different ways of getting just 1 head. Okay, now this probability, we could just use complement rule with it. So 3, 4, 5, we've used 5/8 chance. So that leaves 3/8 left for this one as well. And if we think about just changing that H to a T and these T's to H's, we could see that, the math would be exactly the same as what we just did for the 1 heads. We would just be switching it to the 2 heads and 1 tail scenario. Okay, so here is our probability distribution. Let me get rid of that work. because this one also asks us to graph it. So I'm going to fit the graph on this bottom half here. For this one, we're not going to get a constant distribution like we did for the tossing or rolling a die. So if we list out the x values across the x-axis, these are our random variables. And if I come up with a scale, I'm just going to count by 1/8. So that's 1/8, 2/8, 3/8. And if we make our bars 1/8, 3/8, those are all supposed to be evenly or have even widths there. This one looks a lot smaller than my other three. But we see that it is more of a symmetric distribution. And not constant. Okay, there are two requirements for any probability distribution that you make. The first one, the sum of the probabilities always have to add to 1. And then the second rule is that each individual probability has to be valid. So that means that they have to be in between the numbers from 0 to 1. We can't have negative probabilities or probabilities that are greater than 1. Those probabilities are technically not probabilities, they're impossible. So we do have to have a valid probability for each outcome in the sample space. Okay, the next thing that we're going to talk about is how to find the mean of that probability distribution. So here's what our formula looks like. Notice that we're using the Greek letter mu to represent the mean. That is because we're listing all the possible outcomes. So this is technically a population mean and not a sample mean. So we no longer use X bar because it's not a sample, it's a population. So we use the Greek letter mu. This formula says that we multiply X times P of X and then sum those products together. So add up those products. So we're going to go through that for the probability distribution that we just made a second ago with the number of heads when you toss a coin 3 times. So we've already written out this probability distribution. So hopefully you guys already have that written down, and we're just going to practice using this formula. So this part says that we're going to multiply X times P of X. So the first X value is 0, and we're multiplying that by the probability associated with that, which is 1/8. So 0 times 1/8 is 0. For the next random variable, we had 1 is the X value. The probability is 3/8. So we're taking 1 times 3/8 to get 3/8. So notice we're just multiplying straight down here. 2 times 3/8, that makes 6/8. And 3 times an eighth, that gives me 3/8. I've already put those plus signs in here, guys, but that's what this summation symbol stands for. We add up those to find the mean. So if I add up those fractions, I get 12/8. Now it might make more sense to go ahead and divide that, and we see 1.5 is the average, which makes sense because this is a symmetric distribution. So it would make sense that our mean is right in the middle at 1.5. Okay, we also may have to find standard deviation and variance for probability distributions. So I've included those formulas here. Again, notice the Greek letters now, because these are population values and not sample values. So this symbol stands for population standard deviation. And this is our population variance. Okay, again, we're going to compute that for the probability distribution that we just looked at a second ago, dealing with tossing the 3 coins. So again, I am just getting that back on this slide. Okay, what we do first is we multiply x squared times p of x. So I'm going to square these x values before we multiply down. So I'm going to take 0 squared, 1 squared, 2 squared, and 3 squared. Before we multiply down, so 0 squared, that's still 0, times an eighth gives me, 0. What am I saying here? 0 times anything is still 0. Okay, this next one, 1 squared, is still 1. Multiplying straight down, 1 times 3/8, I get 3/8. 2 squared is 4 times 3/8, that gives me 12/8. And 3 squared is 9 times an eighth, that gives me 9/8. So we've just performed this portion of the formula. We still add them together. So we're going to add those straight across. But then we can't forget that we're going to subtract off the mean squared, which remember, we calculated the mean in the last slide. The mean was 1.5. So after I add these together, I'm going to subtract off 1.5 squared. Okay, let's do that math. So if we add these together, I'm getting 24/8, right? 24/8, and I'm going to subtract off 1.5 squared. Now, 24/8 is just 3. Sorry, I'm out of room here. Let me hide this, actually. There we go. So that's 3, and I'm subtracting off 1.5 squared. So 1.5 squared gives me 2.25. So if we take 3 and subtract 2.25, it gives me 0.75. Now, 0.75 is the variance. We've been calculating the variance. So in order to find the standard deviation, I would square root that. Okay, so our variance for this example is 0.75, and our standard deviation is going to be the square root of 0.75. Let me do that. Oops, I just took the square root of 2.25. So let me try that again. Square root of 0.75. And we get 0.87 if I round that to 2 decimal places. Okay, so our variance is 0.75 and our standard deviation is 0.87. Okay, we are going to form another probability distribution for the sum of 2 dice and then calculate the mean, variance, and standard deviation of that probability distribution. So if we think about tossing or rolling 2 dice, and the sums that we could possibly get, the smallest sum would be rolling 2 ones, so that'd be a sum of 2. And we could get all of these various sums. If we think about the largest possible sum, that would be rolling 2 6s, and that would be the sum of 12. Okay, now there is a pattern to this. So if we think about rolling a 1 and a 1 to get that 2, that's just one chance out of 36 possible outcomes. Over here, the 6 and 6, that would be, again, just one outcome out of 36. But when we move to a sum of 3, we could get a sum of 3 by rolling a 1 and a 2, or a 2 and a 1. So there's actually 2 chances of getting the 3. The 4, we could roll a 1 and a 3 and a 1, or a 2 and a 2. So there are 3 chances out of 36. The 5, 1 and a 4, 4 and a 1, 2 and a 3, 3 and a 2. So there are 4 chances. Hopefully we're noticing that those are increasing by 1. they will continue to increase by 1 until we get to a sum of 7. That is the most frequent sum when you roll 2 dice, and it has a chance of 6 out of 36. And then it starts to decrease back down. So this is 5, 4, 3, 2. If you add those numerators together, ladies and gentlemen, that's how you get that total number of possible outcomes, which is 36. You could also find that by thinking about how many outcomes I have when I roll the first die. There are 6. And then the second die, there's still 6 options. We would multiply that to find our total number of possible outcomes. It's 36. Okay, so our probability distribution is kind of large there. I don't think anyone really wants to be finding those means and standard deviation by hand. So we're going to go over the calculator steps now. I just press Stat and then Edit. And I'm going to enter those X values into list 1, just like we did for frequency distributions before. And when we were calculating means and standard deviations for data sets. Okay, I have my X values entered in list 1. I'm going to go over to list 2 and enter those probabilities. So 1 divided by 36, 2 divided by 36. I'm going to do that for each of those probabilities. So this will take me just a second. Remember that they increase by 1 until we get to that sum of 7, which has a probability of 1/6, 6 out of 36. And then they decrease back down. To 1 out of 36 for that sum of 12. Okay, the steps are going to be familiar. We're going to go to Stat, over to Calc, and it's still that very first one var stats. We do have 2 lists, so we need to tell the calculator that we're using the X list, list 1, and the frequency list, or probabilities, are in list 2. And we're going to calculate. Okay, for this distribution, we find that the mean, now we do have to remember that we're not going to write X bar, we're going to write mu, because these are all of the possible sums that we could get when we roll 2 dice. So it technically is representing a population and not a sample. Our mean is 7. The calculator knows that this is not a sample standard deviation, so it's going to leave that blank for you. Our standard deviation is of the population, and that's 2.42 if I round that to 2 decimal places. And the calculator does not tell us the variance, so we are going to square that number to find it. So 2.42, there is going to be a little bit of rounding error there. So it's 5.89 is the variance. Okay, this last slide is a you try. I'm asking you to take a look at that example, pause the video here, and then when you think you have the solution to that, go ahead and unpause the video to get the solution. Okay, hopefully you pause the video and you have similar results as I do on the screen. We have, as far as showing the number of jacks, we have the random variables 0 jacks, 1 jack, or both jacks. The probability of getting no jacks, 48 out of 52 times 47 out of 51. That I rounded that to 0.85, so there is a little bit of rounding error here. I did the probability of 2 jacks next, so probability of jack on the first draw is 4 out of 52 times the second draw is 3 out of 51. That gave me 0.005, again a little bit of rounding there. And then I used complement rule for the 1 jack because Again, I want these to add up to 1, but also thinking about the probability of getting 1 jack, I could get the jack on the first draw and then a non-jack on the second draw, or I could get the non-jack first and then the jack. So that seemed like a lot of work. So I just added the 0.85 and the 0.005 together to get 0.855, and then subtracted that from 1, use complement rule. So that gave me that 0.145. I graphed that here, and we can see that 0 is much more common than the 1 or the 2, so it's extremely right skewed. It has a mean of 0.155, a standard deviation of 0.38, and a variance of 0.14. Okay, this concludes the lesson on probability distributions.